Good morning, I'm Adam Lazinski. Along with me, I have Matthew Johansson, Andrew Zoflik, Denzel Boham, and Jessica Nywar. Our faculty advisor is Dr. Hinovich, and our industry advisors are Larry Weiler and Nate Case. Together, we're Team 16 Schramm Manufacturing Improvements. For this project, we work directly with Schramm Incorporated, a company located in Westchester, Pennsylvania. They are a leading manufacturer in the hydraulic drilling rig industry. They not only sell their rigs across the United States, but they also sell internationally in the countries such as India and Australia. In order to understand this project, I need to define two terms. The first one is a top head. The top head is the mechanical component of the drilling rig that drives the drill bit into the ground. The second term is a slabback. The slabback cradles the top head and allows it to slide up and down the mast. It also allows the top head to pivot while loading and unloading piping. So both of these components work in conjunction with one another, and as the rig is in use, they slide down the mast, add piping into the ground, and natural resources can be extracted as necessary. By referring to the figures, you'll see that the mast is a tall white vertical structure, and the top head and slabback are the yellow components attached to the mast. Currently at Schramm, the slabback lacks a designated assembly cell area. It also lacks adequate tooling to efficiently assemble the process. On the other hand, the top head does have an assembly cell area, but due to inefficiencies, there are several areas that could use improvements. There are two main objectives for our project. The first one is to design a slabback assembly fixture to increase the efficiency of the slabback assembly process, and the second objective is to create assembly cells for the top head and the slabback to increase efficiency, productivity, and safety of the entire manufacturing process. We also conducted lighting optimization within the future cell building. Now I'm going to switch over and talk about our slabback design fixture. The design criteria that had to be met are as follows. It needed to be compatible with 5 different slabbacks at Schramm. It must be able to support a load of up to 14,000 pounds. It must not have any deflections greater than 30 thousandths of an inch or stresses greater than 25 KSI. It will need to be easily transported throughout Schramm's 27-acre facility, and it will need to be made at Schramm using their own equipment. And now I'm going to pass it off to Matt to talk more about this fixture.
Thank you, Adam. For our slabback assembly fixture, we started off with 3 conceptual designs. These designs were developed and consolidated to create our initial full design. This design incorporated ergonomic qualities to allow for an easy assembly process for the workers. This design was used for our initial design validation. The materials used in our fixture were selected from the inventory available at Schramm. For the plates, we chose ASTM A36, which is a strong, mild steel with high availability. For the beams in our fixture, we chose ASTM A572 grade 50, which has a high yield strength and durability. The reason we chose this material for our fixture is because beams comprise the largest amount of our fixture, and we wanted to ensure that it would be able to sustain the required loading. For the tubes in our fixture, we chose ASTM A500, which is a highly durable and available steel and is the standard steel for tubes at Schramm. Schramm conducted an initial FEA of our fixture, and we held several design reviews with the assembly workers. Through these 2 things, we found a number of items that needed to be addressed. The first item was the structural integrity of the fixture. To address this, we added a support cylinder in the center of the fixture to reduce the deflection. We also added some support plates inside the flange of the beam to increase their structural integrity. We also optimized the assembly workspace by lowering the overall height of the fixture by 7 inches, allowing greater access to the top of the slabback for the assembly workers. We also increased the forklift accessibility, and we did this by widening the tubes of the fixture to allow all of the forklifts at Schramm to easily move our fixture around their campus. All of these things were incorporated into our final design. As you can see to the right, the assembly process is outlined. The top picture is just our fixture by itself. The second picture is our fixture with the slabback, which is held in place by the 2 top plates, as you can see on the fixture. And the last picture is the slabback and top head fully assembled on our fixture. I would now like to pass it off to Andrew to talk about the analysis that was done. fixture.
Thank you, Matt. With the analysis for our fixture, some of the initial requirements that we had were talked about previously with Adam having our deflection and our stress. With this, our initial full design did not meet our initial design criteria. With this, as you can see on the picture on the left, that the greatest deflection occurred mid-span of our loading plate. With the optimizations that Matt talked about, we had the result of our final design. With our final design, it was well within the design criteria, and with this, we did additional risk assessment by adding more weight, which is why the maximum deflection locations from the picture on your right and your left vary. Now I'd like to change gears and move into our top head and assembly cell fixtures with how we improve them. With this, the current slide back assembly cell had no designated area like Adam mentioned. Also, the current top head assembly cell had a designated location, but it was in need of upgrades. We wanted to implement lean manufacturing techniques to increase the efficiency of these cells. Lean manufacturing is a method to optimize the production process and eliminate waste. Using this methodology, we ended up coming up with our proposed cell. The design criteria we had was to make sure that all tools, inventory, and machinery were all included within those cells. We also wanted to provide adequate shelving space around the perimeter, as you can see from the 3D rendering. With this, we also wanted to provide a smooth path for assembly. To the left of the yellow crane, you can see that that is our top head assembly cell, and to the right of the yellow crane, that is our slide back assembly cell. Once the top head and the slide back were manufactured, the top head would get integrated into the slide back while still being on our fixture, and from there it would move to the next step of the assembly process. Some of the benefits that came along with our proposed cell was there an estimated 45 man-hours to be saved per assembly. Along with this, we were consolidating the top head and slide back cell to one location. As you can see from location 1, that was the current top head location, and as you can see from location 2, that was the general location for the slide back cell. Those both were moved to a new assembly area indicated by the star. With this, we want to make sure that all items were within close proximity to the fixture along with the workers. That directly ties into making sure every implementation we made met lean manufacturing requirements. And with this, I'd like to pass it to Denzel with the lighting analysis and proposal for these cells.
Thank you, Andrew. In the assembly building that Andrew was just referring to, we performed a lighting analysis. We know for a manufacturing setting like this, there needs to be 300 to 750 lux. And lux is lumens per meter squared. We took 26 light readings in the building. 4 of these 26 readings were below this requirement. 10 of the 26 readings were below 500 lux, which is about the midpoint of this range. We also knew that several of these readings were higher due to the sunlight coming through the windows alongside of the building. We investigated several light bulbs, the first being sodium light bulb, which is what's currently used at Schramm. We also looked into a fluorescent light bulb and a LED light bulb. We used MATLAB to perform this analysis. Here's some of our assumptions. We assumed that lux can be approximated as the number of lumens, or lumens per or meter squared. And R is the distance from the light bulb. We also assumed a light angle of 90 degrees. And this is illustrated in the photo below. We know that the manufacturer's rating, lumens rating for each light bulb is not going to hold for the entire life of the light bulb. For this reason, we use an average light lumens output for the analysis. The 3 figures on this slide show a lighting map of the assembly building with the different light bulbs. The light location is represented as black circles, and the assembly cells is marked off with a red line. The scale for the graph is the dimmest spots in the building being black and the brighter spots being white. Looking at the 3 graphs, you can see that the LED lighting option is brighter, if not as bright as the other 2 options. And in fact, on average, the LED is 10% brighter than the sodium light bulbs currently used in Schramm and 30% brighter than the fluorescent light bulb. For this reason, we can conclude that the LED light bulb would be the best choice based solely on the lumens for the different light bulbs. We also performed a cost analysis to look into the money side of this. And I'm going to pass it to Jess to talk a little more about this.
Thank you, Denzel. For our lighting cost analysis, there were several assumptions and considerations. First, we assumed an 8-hour daily runtime for each of their lighting units, with 24 lighting units assumed for each of our lighting methods that we are going to analyze. We then assumed installation costs for each of the lighting methods that are not currently installed on Schramm's campus, as well as replacement costs per light bulb for every time a light bulb goes out. In addition to this, we also assumed and calculated the associated labor wage costs for every time a maintenance worker has to perform maintenance or replace a light bulb. As you can see in the table, LED lighting proves to be the best method based on lifetime in hours as well as cost per year. Moving forward, we were able to figure out that LED lighting provides the greatest cost reduction at about $10,000 savings annually, with an associated $24,000 installation cost. But as you can see, after the break-even point at about 2 years, LED lighting proves to be the most cost-effective method. In conclusion, for our project, there were several things that we would like to contribute or have contributed. First, we designed a low-cost universal assembly fixture, which satisfied all of our design criteria and can be used by Schramm in the future for all of their product lines. Second, we designed an ergonomic slieback and top head assembly cell layout. This consolidates and organizes all of their inventory into one centralized location, and as stated before, has an estimated 45 man-hours savings per assembly. Lastly, we proposed a new lighting system using LED lights. This, again, provides an estimated $10,000 cost savings per year. Overall, the two things that we are contributing are the slieback assembly fixtures, which are ready to be manufactured by Schramm, as well as the assembly cells, which are ready to be implemented at Schramm's discretion. Now I would like to pass it off to Adam with our acknowledgments.
There are several people we would like to thank for helping us out with our senior project this year. Those people include our industry advisors at Schramm Incorporated, as well as our faculty advisors here at Widener University. And now I'd like to open it up to any questions.
All right, about 3 minutes for questions. Does anyone have any? Yes.
So what was your production rate per unit? I understand you say 45 man-hours in your actual production of the parts, but how many are you actually producing within the amount of time, like a week, say?
Schramm can, it was 45 man-hours saved per assembly. So Schramm, it depends on their production time on a week-to-week basis. So they could assemble, the 45 man-hours was a savings for just one assembly. So a top head and a slabback just for one of their drilling rigs.
And how many people will be working on the assembly?
About 1 or 2 people, depending on how many people would be there during the shift.
Yes, in the back.
What exactly will your product be used for?
Basically, the purpose of it is to aid in the assembly process by creating a safer environment for the workers. It's basically just a fixture as these things are being assembled. It's to hold them securely due to their size and allow for a more streamlined and consistent assembly process.
How much of your design was based on input from the shop floor workers who are going to be using the equipment?
The majority of our design was based off that. We had multiple design reviews with the shop workers and the shop foremen to make sure that we got their full input while we were making the cell and the fixture, which ties directly with lean manufacturing, making sure that everything they were going to be doing and their methods were as efficient as they could be.
Yes.
What was your biggest struggle throughout the whole thing?
I would say just the fact that going through the entire design process and getting our design to the point to where the shop workers were completely satisfied, because at the end of the day, they're the ones that had to work with it.
All right, let's give our team a round of applause again.